Good morning, Physics 20. I hope you guys are all having a good day today. Welcome back, and we're going to be looking at wave interference and superposition today. So please enjoy the pun. It is pretty good. All right. So today, ladies and gentlemen, we're looking at a very practical element of waves. This is something that is that applies to technology used in your noise-canceling headphones or earbuds, and this is something that is used in with light waves as well. Like it's a really cool aspect of waves, and it explains why when you go into a really noisy room, you can't hear things properly because you're having waves overlapping at different times. So it's really cool. It's pretty cool. All right, so ladies and gentlemen, what the whole concept of this is to look at what happens when two waves bump into each other. Okay, so the concept is called interference, and it is what occurs when waves are going to cross paths with another wave as they're going to travel through their medium. So these waves are going to pass through the same place at the same time. And what they're going to do is they're going to follow what is called the principle of superposition. Now, superposition essentially means the waves are going to overlap each other. It's going to predict the new shape and new amplitude of the wave when they are going to come into each other. So, ladies and gentlemen, lesson subtle hint, this piece is important. It states that the amplitude of the combined waves at each point of interference is the sum of the amplitudes of the individual waves. So the individual waves are going to add to each other. All right? All right. So this is a really nice example here. I quite like this one. It looks like it's a little bit of a mess, but we're going to go over this example in a little bit more detail here. So what we happen to have is we have two waves, and they're moseying along down the same spring. Okay, I'm going to give these waves like ultra fancy names. We'll call this wave the red wave. Okay. And then I will call this guy the blue wave. Very fancy names. So blue wave is going to be moving this way down the spring, while red wave is moving this way down the spring. Now, the thing is that when these waves are going to come up to each other, their amplitudes is going to add on top of the other. So let's use green here to remind you what the amplitude is. The amplitude is the height of the wave. So in context of a sound wave, it's going to be how loud that sound is. Okay? So when this blue wave is going to come in contact with this red wave here, guess what's going to happen? Okay? Well, this blue wave, it's still technically, it's going to be, that's where it would be if there was no other wave, okay? Well, its amplitude is going to be X at that point. All right, now if there was no other wave present, the red wave would be like that. Well, however, ladies and gentlemen, that's not going to do here. These waves are going to add to each other. So I'm going to call this the purple wave because we're blending red and blue. So what the purple wave is going to be what actually you see. It would look like that. Okay, now we're adding this wave to this wave. Okay, well, as the red wave is going to continue doing its thing and moving down the spring, this is where the red wave actually would be. Okay. This, if it was by itself, this is where the blue wave, that's more purple, this is where the blue wave would be if there was no red wave. However, ladies and gentlemen, because they're overlapping, they're in the same place at the same time, their amplitudes are going to add. So what we're actually going to see is we're going to see the purple wave here. So the adding of these two. All right. So as these waves are going to continue moseying along, doing their thing. So there's our red wave, excuse me. Although a dotted line, well, that's where the red wave would be if there was no blue wave. Well, the blue wave would be here if there was no red wave. But because they're in the same place at the same time, what do? We add them. We add the amplitudes. So we're going to wind up with this purple wave adding between them. Okay? So that, ladies and gentlemen, is essentially the law of superposition. The waves are going to add as they collide. All right? All right. So we're going to look at this in a little bit more detail, a little more specifically, about the two types of interference. So how these waves can interact with each other. So to keep consistent here, our amplitude of the crests, we consider them to be positive, and the amplitude of the troughs, we consider them to be negative, just for sake of ease. Now, when you're going to have two waves overlap, our resultant wave is going to be greater than the amplitude of the waves. That is called constructive interference. So this means you have two crests or two troughs overlapping. The example that we looked up here, we had two crests. So we wound up with the amplitude being larger. These waves were in phase. We had two crests that overlapped. Okay? It is going to be constructive interference. So think of constructive interference as two people who are very talented at singing, and they're going to hit that exact same note at that exact same time. And then what's going to happen is the two waves are going to add over top of each other, and the sound wave is going to be louder. Okay, so that is why when you have a whole choir singing, is that it's loud. It's because these waves are overlapping. Whereas when you have just one person singing, you have only the one set of peaks and troughs. Cool, hey? Yeah, it's pretty cool. All right, so constructive interference, when two waves are going to add to get a greater amplitude. So now we're going to go and look at destructive interference. Now, destructive interference is when you have the resultant wave has less of an amplitude than the original waves. So destructive interference is when you have a trough from one wave and a crest from another, and they're going to cancel each other out because they're out of phase. Now, this is some of the technology used in your noise canceling headphones. So, like the really fancy ones that are made by what's the company, Bose or something like that. And they use the concept of destructive interference to cancel out background noise. If you look on Google Classroom, I've included a YouTube video that explains how noise canceling headphones work through the concept of destructive interference and a bit of history on the technology of noise canceling. Cool, hey? All right. So, ladies and gentlemen, what we're going to be doing is we're going to be looking at a couple examples here of both constructive and destructive interference. Okay, so this column here on the left is our example of constructive interference, and this column here on the left is an example of destructive interference. Okay, so I'm going to just put a little dotted line down here, so then that way it's easier to separate the two sets of waves here. So we're going to go and use our fancy purple wave and blue wave concept again, and red wave. So here we go. We've got, this is wave number one. We'll make this guy the red wave. Okay, so the red wave is going to scoot this way. We're going to say he's got an amplitude of, I don't know, let's make it 2. We're going to say this guy here, we're going to make him the blue wave, so I won't give him a color over him. It's already blue. Let's say he's got an amplitude of 3. Okay, well, red wave and blue wave are moseying along down the line. Well, as they overlap and we get a purple wave, so the combination of these two amplitudes, well, guess what, ladies and gentlemen? If this is 2 and this is 3 and we've added the amplitudes, what's this going to be? An amplitude of 5. We add the amplitudes of each wave. Well, then the waves keep going along their merry way, and red wave continues off and blue wave continues off, and blue wave still has its amplitude of 3, and red wave still has its amplitude of 2. All right? Okay. So that's constructive interference, where they are going to add to each other. Well, now we've got a new scenario here. Red wave is moseying along here, and red wave is going to have an amplitude of 2. Well, look at what we have here. Our blue wave is now a trough. He's got an amplitude of, let's say, -3, and we call troughs negative and crests positive. Okay, so red wave continues to mosey along, blue wave continues to mosey along, 2 and -3. Well, when we have two waves arrive and overlap, our purple wave here, so our combination of both waves, is going to have an amplitude of, if you say -1, you are correct, because we have added 2 and -3. So that means our amplitude is -1. Well, red wave continues on his merry way with his amplitude of 2, and blue wave continues on his merry way with an amplitude of -3. All right? Okay. So, ladies and gentlemen, when we apply destructive interference to your noise-canceling headphones, what the technology is doing is trying to match the frequency of the sound that's coming in, but instead of making a peak, it's making a trough, so that way they cancel. Neat, eh? Yeah, it's pretty cool. Pretty cool. All right. So, ladies and gentlemen, this is just a very interesting pattern created by an interference pattern created by two waves that are right next to each other. So, these losses is if you're viewing the wave from above. And these lines here, these solid lines are peaks, okay? These dotted lines are troughs, okay? So then you can get some very unique patterns of interference when the waves overlap each other. So what you would do is you would look for where the solid lines overlap, and that's where you're going to get constructive interference, or a line of where the waves peaks overlap and crests overlap. Try this again. Crests overlap and troughs overlap. There we go. So right here, that's what this line is, but you can do this anywhere. So if I go here, okay, well look, I've got a crest and a crest overlapping here. I've got a trough and a trough overlapping here. Crest and a crest, trough and a trough, crest and a crest. So what I have is I've got a line of constructive interference running along this way. Okay, so that is where I'm going to have larger waves. And anywhere where you are going to see a crest and a trough overlapping is going to be destructive interference, where you're going to see no waves or smaller waves. So, for example, oh, well, look here. I've got a trough with that dotted line and a crest with that solid line. A crest and a trough. And then I've got a crest and a trough, crest and a trough, crest and a trough, crest and a trough. And then, so when that lines up, that's where my destructive interference is going to be. So I wouldn't worry too much about this particular pattern just yet. We're going to be covering it more next year when we are going to be looking at light waves and how interference works with diffraction. All right. So, ladies and gentlemen, I hope you guys all have a good day. We've got some practice problems there. So give some of those a shot. And I hope you enjoyed this lesson and that it didn't interfere too much with your schedule. Got it? Interference. Had to happen. All right, ladies and gentlemen, no fires, injuries, or explosions. Have a good rest of your day. Bye.